Hi everyone. So today we're gonna go over the homework. So I'm gonna quickly record this to kind of go over like what we should be doing and stuff like that. So let me kind of get this ball rolling. So basically what we have, this is actually not too difficult. The hard part was kind of reading it. So I kind of wanted to go back to week two and week one when we were talking about how to read problems. So the main difficulty is figuring out what this kind of means. It takes up to 9 seconds to arrive, and that at most two balls arrive between the 405th and 413th second. So if I try to write this out by events, which is what we had before, I would say the probability that, that's the P, the fourth ball takes up to 9 seconds to arrive. And so here we'll use commas instead of intersection. At most, two balls arrive between 405th. I should 405th and 413th second. So let's look at some variables to kind of help us out. So we'll let x be, what did I write? Be the time it takes the fourth ball to arrive. And we're going to let y be the number of balls, that arrive between 405th and 413th second. So notice how in this case we're basically looking at this is for x and this is for y. So in other words, what this is translating to, I'm trying to solve when x takes up to 9 seconds. So x has to be less than or equal to 9. And when y, we have at most 2. So y also has to be less than or equal to 2. And here the kind of thing to note is that these are independent. They're independent events, right? The time between the 405th and the 413th second, the number of balls that arrive between those two things has nothing to do with how long it takes the first four balls to arrive. They're two totally different things. And so they're independent events. So really we can solve these separately. This first one is basically Erlang distribution. So this is Erlang. Which basically means that we have to do our integration, right? So we're going from 0 to 9, from now until 9 seconds, because 9 is the maximum. E to the minus lambda x, and I haven't really gone over what lambda is yet, but that's okay. R, x r minus 1, all over r minus 1 factorial dx. So in this case, what's our lambda, what's our r? Well, we have 4 balls, so what we're doing is waiting for ball 1, then ball 2, then ball 3, then ball 4. So this is saying r is equal to 4 since we have 4 balls. What's our lambda? Lambda is just going to be our average. And so what is our average? We know that there's 12 balls per minute. But notice how everywhere I have seconds. So let's kind of convert this into seconds. So if it's 12 balls per minute, how many is that per second? What this means is we get 1 ball every 5 seconds, right? So 12 balls per minute means 12 balls per 60 seconds, which means 1 ball every 5 seconds. So in other words, notice how I have 1 over 5. So this means lambda is equal to 1/5. So in other words, I just need to calculate this integral. E to the minus 1/5 x 1/5, r is 4. x to the 4 minus 1 all over 4 minus 1 factorial dx. I won't, obviously, so I'm not going to solve this like by hand. I'm not going to do integration by parts. I think we've seen this quite a few times. But in essence, what you should end up getting is 1/5 to the 4th times 1 over 3 factorial. And then you should have minus 5x cubed e to the minus x over 5 minus 75x squared e to the minus x over 5, because this also won't help you since everyone has different versions. But you should get something like this. And if you use the tail formula, that's okay. You just might have things done a tiny bit differently. Over 5 from 0 to 9. Plugging these in, what we end up getting is, I'll just go straight to the final answer. 70839. So we end up getting this for p is x less than or equal to 9. So next up, we have to figure out what p of y less than or equal to 2 is. So what is this? Here, this is calculating the number of balls between some number of seconds. So since I have an interval and I'm counting the number of balls, this should make you think Poisson. So here we have a Poisson distribution. And remember what Poisson is. Well, first we need to calculate our mu, and we have to know kind of how far we're doing, right? So, so technically what this is e to the minus mu. We're going up to 2, so I should have mu to the 0 over 0 factorial, plus mu to the 1 over 1 factorial, plus mu to the 2 over 2 factorial. So mu, if you recall, what this is the average times the length of our interval. In other words, it's lambda times t. Our lambda we already have from the 4. This is 1/5. And our t, this is length of interval, right? Everything has to be in seconds. So since our interval is between 405 and 413, what we have is 413 minus 405, which is 8. So it's times 8. So my mu in this case is 8/5. So at this point, you just plug mu in. So e to the minus 8/5, 8/5 to the 0 over 0 factorial, plus 8/5 to the 1 over 1 factorial, plus 8/5 to the 2 over 2 factorial. And then plugging this into the calculator, what you should end up getting is roughly 0.78335849. And so what we end up having is, remember the thing we're trying to solve is this. This is equal to this by independence. And here we just have to plug in our numbers. 9 times 0.78335849. And so what we end up getting is, if we did this multiplication, we would get 0.085155764. And that is our final answer. So it's not too bad. The probably tricky part here is just to figure out what needs to be plugged in where. And that these are just independent because they don't really rely on one another, which means we can just separate them out. So that was kind of the only tricky part. Other than that, I think we had seen Erlang 1.5 million times. We had seen Poisson 1.5 million times. So this should be things that we kind of are used to, especially since we had also gone over Poisson point process quite a few times. All right, that's it for this video. I hope everyone had a good exam too. Oh, I should go up so you can actually see this. I hope everyone had a good exam too. I will see you all next week. There's no homework next week, which is good. And yeah, that's it. I'll see you later. Bye.